We present RefFusion, reference-adapted diffusion models for 3D scene Inpainting. Our framework personalizes image diffusion models on reference images, transferring the adapted knowledge to 3D scenes for various downstream 3D editing tasks. Let's begin with 3D Inpainting as an example. Assume we have captured this Gaussian splitting scene and decided to remove the was and the dark disk underneath it. We assume the rough masks annotating the edit region corresponding to each of the training views is given. These masks can be obtained by any off-the-shelf 2D or 3D segmentation methods. After obtaining masks, controlling Inpainted scene generation can be achieved by conditioning on text prompts. However, we contend that text is a weak signal for 3D control. We instead ask the user to provide their desired output in the form of one or more reference views. In the case of scene Inpainting, the user can use their preferred image Inpainting method and show us an Inpainted reference view. So our inputs are the training views, their corresponding masks, and one or more reference views showing the target. We further assume that a set of 3D Gaussians from the original scene is also given. The initial stage of our method involves fine-tuning the diffusion model on the reference view. We initiate this process by augmenting the reference view to construct a dataset, extracting global samples by cropping thin borders around it. This dataset is employed for fine-tuning a pre-trained diffusion model. For scene Inpainting, we utilize an Inpainting diffusion model. In each iteration, a random set of global crops is sampled, accompanied by a random rectangular mask. The noise prediction is conditioned on a constant phrase, a photo of SKS. Subsequently, we calculate the diffusion loss, anticipating the generation of the input image to refine the diffusion model. We concurrently fine-tune the diffusion model on local crops around the masked region of the reference view. This process imparts knowledge about the details and textures of the reference view to the diffusion model. It's noteworthy that we utilize a slightly different text prompt for the local crops. The second stage of our method involves distilling knowledge from the adapted diffusion model to the scene. We commence this stage with the pre-trained Gaussians. Preceding the optimization phase, we eliminate the Gaussians, mask the cross views, and substitute them using the reference view and its predicted depth obtained from a monocular depth estimator. During the optimization stage, at each iteration, a random view is sampled. We render the appearance and the depth of the scene using the current set of Gaussians. The score distillation sampling loss is then employed to supervise the masked region using the adapted diffusion model. For the unmasked pixels, we simply employ the reconstruction loss. To further eliminate the remaining artifacts, we utilize the discriminator to compute the adversarial loss. To safeguard against degenerate solutions in geometry, we introduced randomly selected views inpainted using the adapted diffusion model to an off-the-shelf monocular depth estimator. We supervise the depth of the scene based on the estimations obtained. Note that all the losses other than the reconstruction loss may have adverse effects on the quality of the unmasked region. To mitigate this, we monitor the Gaussians representing the masked and unmasked regions separately and only update each set using their respective losses. Here's the Inpainted scene for this specific example, showcasing the preserved quality of the background and the accurately matched Inpainted content as indicated in the reference view. Now let's explore a few more examples. In this scene, the objective is to remove the water pot. The scene optimization presented in a sped-up video for better visualization effectively removes the water pot. The original scene including the unwanted object, which is the water pot, looks like this. The output of our model for the object removal task produces a scene without the water pot. Observe the precise reconstruction on the porch behind the removed object and the faithful representation of the texture on the wooden bench. By simply changing the reference view to an image featuring a different object, such as a donut instead of the water pot, our model inserts a 3D donut into the scene. As an additional downstream task, we demonstrate our model's capability to outpaint scenes. In this scenario, we mask out a sphere in the middle of the scene, invert the masks, and instruct our method to outpaint the scene using a single ground truth image from the original scene as reference. In another example, the goal is to remove the book from the top of the desk, and here is how our model inpaints the scene. Similarly, we can effortlessly insert new objects like this flower pot by changing the reference view. In this instance, the objective is to remove the backpack. Our model successfully removes the backpack from the scene. For reference, here are the outputs of some of the baselines on the same scene. This one is using the same SDXL reference view as our model. We also compare to a concurrent unpublished work in Paint 3D. We showcase the versatility of our method in a distinct application, specifically sparse view scene completion or authentic scene completion. Consider a scenario where we have captured and reconstructed a scene and aim to remove a cardboard box. This time, we possess a few images from the scene without the object. The task is to fill the target region based on sparse view supervision available from ground truth images. Having ground truth values for sparse views, we can use the reconstruction loss of 3D Gaussian splatting or 3D-GS to fill the missing region. However, as Gaussian splatting requires a larger supervision dataset, its quality diminishes when only a few images are available. Going from a single training view to 2 training views doesn't significantly improve the outcome. In contrast, by adapting a diffusion model on a ground truth view and incorporating our guidance losses, including local and global SDS losses, depth loss, and adversarial loss, our model successfully fills the masked region even when only a single ground truth view is available, exhibiting high fidelity to the ground truth content. The results improve further with more views provided to our method. Here, we present a side-by-side comparison of 3D Gaussian splatting results at the top and our results at the bottom. As illustrated here, in the sparse view setting, our method represented by the green line consistently produces superior results in terms of LPIPs and PSNR when compared to 3D-GS.